Am I audible now? Yeah, my microphone is actually turned on. Can you try checking your audio once? Can you try joining once again?
Sir, your microphone is off, sir. I don't know why.
I can hear you now, but you're not able to hear me. Yeah, is it audible now?
Yes, sir. Yes, sir. Now it is audible.
Okay. Yeah, so were you asking something previously?
Sir?
Did you ask, like you raised a hand, is it because you are not able to hear?
Yes, sir. Yes, sir. That's why I raised that.
Okay. Yeah, so okay, just to repeat, okay, I think since it's not audible, what I was trying to discuss is just a continuation of where we stopped in the last week. So we have three different grids: one for pressure, horizontal component, and vertical component of velocities. The first one is a cell-centered one. The second U grid is all the face-centered, only on the horizontal faces, and the V grid is only on the vertical faces. So these are the matrices that I will be storing. Just to be consistent with the programming that we will be like, we will see how to implement it programmatically. So it's better if we use the indices notation so that you can directly use your arrays. So if your current cell is I comma j, your each cell I am using I plus 1. And similarly for the face centers, it's basically you are incrementing by only half, so I am writing I plus half and j plus half for east and north face respectively. So the integration goes in this way. So for your x, you will be integrating from west face, that is xi minus half, to xi plus half is your east face, but your j will remain the same. Or let's not confuse this here. When we actually implement it, it will be a little easier. So when you do this integration, you will essentially have, for the first part, you have del u del x dx, and then you have an integral dy, you have del v del y dy, and then you have a dx. So this particular integration becomes integration of y will essentially be delta y times your u along the x direction. So you will be moving from I minus half to I plus half, and similarly for the second one it will be delta x times j minus half to j plus half. So essentially left with u I plus 1 I plus half j So this is very similar what we were writing previously. This is east minus west plus north minus south equals 0. So f east, f west, and the remaining two north and south respectively. So discretizing continuity is straightforward. Now when it comes to momentum equation, when we are actually implementing this, so the first step is we give an initial guess of your velocity, and from there you will be able to calculate your f east, f west, f north, and f south. But then we don't use this immediately. We store this in one variable. Say I'll follow the same notation that is used in the class. So P is your mass imbalance. Ideally this has to be 0, but since you are guessing a velocity profile, this will not always be 0, this will give you some finite number, and then we will use it in the next step when you do pressure correction to actually reduce this value, that we will see later. Now for the x momentum, discretizing is straightforward. So since you are already familiar with it, so maybe I will write the equations right directly. So you have, in general, you have your convective diffusion equation where you have rho u. You will be having a phi here, but now we are your phi is your horizontal velocity, so I will just write u. Again here you will be having a phi, but I am writing just the horizontal u, and then some source terms which will not write, or maybe if you want to write, you can write for now. So sc plus sp times vp, sp times phi, but we do not have any source terms as of now, so I am just leaving them. We will write the pressure gradient term. So this is my sc, basically your sp is 0. So now the next steps are again straightforward. You integrate, apply Gauss divergence theorem, and then you will be coming up with f east is basically f I plus half j times ui plus half j north and south this will be equals to your delta y times p ij minus I plus 1j, and then you have your diffusion terms. So if I write d directly, d east times and d west minus up, and then you have other terms, north and south. Now the question comes is to how are these values calculated. Fi is straightforward to calculate. Fi plus half j, or in general any value, can be calculated by since you have some rho times u at that particular I plus half j. Since it is a horizontal one, so you have a delta y. So this is straightforward because your u is stored at the phase centers, so you can calculate these f's. The problem comes with the d, where your, say if you want to calculate di plus half j, this comes a sorry, so okay, it's my mistake. So we are following staggered grid approach. Okay, this is, sorry, we need to correct this. In staggered grid, in collocated you will be using this formulation, but in staggered grid you have your grid completely different. So maybe let's say I'll write a grid first. So when you are trying to discretize here, unlike your continuity equation, you will be discretizing slightly differently. So these are your original cells. So this is the half, you will only consider your phase center like this. So this will be your objective. So this is a cell where you will discretize. So your u is actually stored here. So if this is I comma j, this is I plus half comma j, this is I plus 1 comma j. So the highlighted portion is where you will be discretizing your momentum equation. So when you are essentially writing the discrete equation, so it will be f east is I plus 1 comma j times u east is u I plus 1 comma j minus f west is f I comma j times u I comma j plus north and south are again. So north is How do I get north here? So yeah, so you're saying, so what will be the index notation here?
I plus 1 comma j plus 1 by I plus 1 by 2 comma j plus 1 by 2.
Yeah, I plus half and j plus half times you also calculated at I plus half and j plus half, and then south face is straightforward, so it's I plus half and j minus half. So this times you have your pressure term, delta P is Pi j minus Pi plus 1 j. Since there is a minus, I have just interchanged the signs. And then you have your diffusion terms. On the east face, here comes your, on the east face you need to calculate u at the next one. So if this is I plus half, this is I plus 1, this will be I plus 3 by 2 comma j. So you have u I plus 3 by 2 minus u I plus half j. Similarly on the west face, you'll be having
u I plus 1 by 2 my u
I minus 1 by 2 j minus u I plus half j.
So u plus of j ka minus u minus of j, sir.
Yeah, if I put a minus here, so I'm just directly putting a plus here. So if you put a minus,
Okay, sir. Okay, sir. Okay.
similarly for the north face you have, so this is my north face, this gets a little, okay, we'll see here. So here you have I plus half, j plus half times the velocity should be considered here, so that is u, I will be same, j is incremented by 1. Similarly on the south face, so you have I plus half j minus 1 and I plus half j. So now when you try to collect your terms for A east, so basically you will collect your AP and A and B terms. So AP terms are essentially coefficients of ui plus half j. A east are the coefficients of I plus 3 by 2 comma j. I minus half comma j and A north sorry A north is I plus half comma j plus 1 and south is same yeah AP minus 1. So you need to collect the coefficients of these and then populate your AP east, A west, A north, A south. There the only problem now comes is how do you get your F. I only have the values, previously F values are only calculated at this half indices, but to solve this equation I would be needing the say Fi plus 1 comma j. So like we have discussed previously, you just use an arithmetic mean. So now that we have written in this notation, it will be little easy. So you just write I plus half comma j and then you have and sorry. So an average of I plus half and I plus 3 by 2 will give you I plus 1. So it's like between half and 3 by 2 you have your 1. So similarly for all other indices you will be able to calculate F. Now when it comes to D, it gets a little, D is something that use diffusion coefficients, like as we have started discussing like that, all your pressure, density and your mu or whatever your gamma is only stored at the cell centers. So here D I plus 1 j is essentially the cell centered value at C plus, I plus 1 comma j. That is something that we already store, so you can directly use this, like we are not storing anything at the phase centers. So this is directly you can use. But anyway, like the problems we are discussing are more or less constant coefficients, so you don't have to worry about it. So you directly put dx equal to gamma delta y by del x, or the other one for the vertical direction it will be gamma delta y by delta x by delta y. So D is straightforward. Now comes the velocity components. So the velocities here are so this only these velocities are something that you do not know. So I plus 1j is something that I do not know, because all my u and v are only stored at the half indices. So now I need to again use some kind of a mean to get this value. So it is also similar to this one. So instead of f, you will have a u here. Uij is again, you need to come up with average. Uij is essentially half of
u
I minus half, yes, and I plus half. So this is also straightforward. Now what do I do for this? Ui plus half and j plus half. So basically u is always stored only at the half indices of I, but j are full indices. So if you see here, u is only stored on the horizontal faces, it is not stored on the vertical faces. So each increment will be by delta y, this is delta x. So if this is my I, only for the half indices will come for my horizontal. So this is I plus half, so the next one will be I plus 3 by 2 and so on. But along the vertical direction there won't be any half indices. So you can see that even in this equation. So see, it is I plus half comma j, I minus half comma j. Only along the horizontal direction you will have the half indices, not along the vertical direction for the u velocity. So I plus half is fine, we can calculate, but j plus half is something that we do not know. So again you need to use an average for along the vertical direction. So you need I plus half comma, so since I need j plus half, so I will be taking
k plus 1 and j.
So this is something if you to see on the highlighted portion. So ui plus half and j plus 1 is essentially this component, and j minus 1 is this component. So basically you are taking the north and south neighbors to calculate the value at the cell. Okay, sorry. Ui plus half j is this component and this is this component. So to get a velocity here, you are taking an average of this and this. So it's the same way, whichever way you feel convenient, you can follow that. Similarly, you can get all other velocities, and once you know all the diffusion coefficient, then you solve for these equations. So similarly, you will do for vertical component of the velocity also. So instead of u, you will be having v. Instead of having half indices on the I vertex, you will be having on the j index. That's the only difference. This is something that we stopped in the last class. So now we'll go through the code to see how it is actually implemented. So these are some helper functions which we will not go through. Yeah, so let's, yeah. So you have any questions?
No, sir.
I think you were asking some, okay, we'll come to that also. Once we go through this code, we'll actually see if you have any questions in. So there was one student who asked about how Python, he was not able to implement some of these codes. If there are any issues on that, we can discuss. Otherwise, we'll just continue with this. So as we have discussed now, so x is, this x and y are basically to store the x coordinate and y coordinate. This is straightforward. So this is something different. So when you are actually solving these equations, you will be solving only for your interior cells. So if my cell indexes is from 1 to nx plus 2 and 1 to ny plus 2, my interior cells will be only from 2 to 1. So basically,
your screen is not visible, sir.
okay, so it's presenting actually. Okay, I will just do it again. Is it visible now? I can actually see my other
No.
device. No?
No, sir, it's not visible now.
I can actually see through another device that my screen is visible. Can you try leaving and joining again?
Yes, sir. Now it is visible.
But this is actually not the screen I actually wanted to share. Maybe I will join again. So are you able to see the code now? Is it visible now?
Yes, sir, it is
Visible. Okay. Yeah. So basically, if your indices range from 1 to nx plus 2 and 1 to ny plus 2, your interior cells will only between 2 to nx plus 1 and 2 to ny plus 1. So I'm just storing these matrices J, U and IV basically only for the interior cells so that I can access them easily. And these are the only cells that you will be solving your equations for. IP and JP are for the, so basically this is for your U and V components, and so if you remember, U will be along horizontal faces, V is along vertical faces, and similarly IP and JP are for the cell centroids of P and for your pressure, density and other variables. So this is all the phase values. Now if you see the horizontal faces from 1 to nx plus, since 1 to nx plus 2, out of these the first phase will be a boundary phase and the last phase will be a boundary phase. So anything in between is where your horizontal component of velocity U will be stored, and similarly for the vertical components. So now I've just displayed these are some variables that you will be using: U, V, U star, V star. U star, V star are essentially to store the U and V after solving momentum equation. U prime, V prime are your velocity and velocity corrections. Du, dv are the coefficients in the pressure correction equation. P is your cell pressure and P prime is your pressure correction. So dF is your mass imbalance term. Dx, dy are your diffusion coefficient. D east, d west, d north, d south. So this is your d east, d west term, and that is gamma delta y by delta x. So this is your d north and d south term, gamma dx dy. So I've just put gamma x, gamma y. If you are dealing with some anisotropic media, you will have different values of mu in x and v directions, so I just put 2 terms. Next, coming to your a east, a west, a north, a south, initially I am declaring to be zeros. So these are the values to show your residuals. Residuals are basically when you are trying to solve using, like I am using iterative method, say Gauss-Seidel or something, then you won't be exactly solving it, so you have some residual left. So u residual will store the residual after solving your x momentum equation, v residual along the y momentum equation, and this is p residual is only for your pressure correction equation. So maybe I can ask you a straightforward question: do I require all of this to be 0? Ideally yes, but then because of your nonlinearity, you should not always try to solve completely. So I put a limit on your number of iterations. So if you see, I put a number of iterations. I am limiting the number of iterations to say 500 or whatever number you want. So if you are not keeping an iteration limit, you have to keep your tolerance limits to be a little lower. So instead of 10 power minus 2, you might be say convenient with 10 power minus 6 or some other value, like since we have seen in previous cases where if what happens when you try to change your tolerance and how your bit size will affect your tolerance in Gauss-Seidel method. So if you use a very finer mesh, then your tolerance needs to be finer, otherwise Gauss-Seidel will not give you a correct results. So we have seen that previously. So the first step is you need to solve your x momentum equation. To solve your x momentum equation, you need to update your a east, west, north and south. So how do I do that? So first step is to update your convective fluxes. So F west is basically rho times, like we have seen just now, along the west coefficient, along the west face is Uij, for which I need to, If is stored along the faces. So I am taking U, this is my current face, plus the west will give me the west face. And similarly for the east, I will be taking If and I plus 1. And north and south are similar. So for the south it will be j minus 1 and j, and north it is j and j plus 1. Sorry. Yeah, IFJU and F plus 1 and JU. This is the F is basically, I have written this, so all your halves are taken care of. So because in C++ or in a programming language you usually don't deal with half indices, so I have stored all these values in IF. So it automatically takes care. So basically what I was trying to say is, so when you have IF plus 1, so you have an I plus half cell, this is equivalent to IF of 1. This is something that I have been using in this code. So now as you see, for east and west you will be using the u component of the velocity, and for the north and south phase, the flux, your mass flux will be dependent on v component of velocity instead of u. So it will be v taken along those values. Now once you know F east, west, north and south, the next step is to get your, here diffusion coefficients are not changing from grid to grid, so it is straightforward. Otherwise you need to update your diffusion coefficients also. Here I have been using the hybrid scheme that we have discussed. So if your cell Peclet number is greater than 2, then you use an upwind 1. If it is less than 2, you use a central difference. So this is a programmatic way of writing this. You can check it. So if this particular Fe by D is greater than 2, so one of this will dominate, and then this maximum of this will be 0. So you will be left with minus Fe, or otherwise the other one. Once the coefficients are updated, the next step is to take care of the boundaries. So as we have seen previously, your boundaries will get updated whenever you have a Dirichlet condition. You will have a 2 times dy coming into that boundary, that particular coefficient. So on the south face, okay, I haven't discussed the problem that we are solving. So the problem that I am trying to solve with this code is the boundary layer equations. So if you have a flat plate and a fluid is flowing on top of the plate, so what is the boundary condition you will be having? The boundary conditions you will be having are, the west face will have a uniform velocity, the top face will be having 0 velocity, and the north and east faces I am taking to be high Peclet number assumption. So basically it means they are convection dominant and there is no diffusion. So basically your diffusion flux is 0, something like your Neumann condition for the north and east faces. So whenever you have Neumann conditions, the coefficients for those particular terms should be 0. So on the north and the east face, I am keeping the coefficients to be 0. So the notation for this matrix I am following is, this is my start index. So when the indexing notation is something like this. So if you have an array, so I give the start index along the x direction, and similarly I will give along the y direction. And then I give the value that it has to replace. So if you are familiar with MATLAB, so this is something like so both these statements are equivalent. So this is how you write in MATLAB. This is the notation I am currently following. So what it does, only along the south boundary, all your AS coefficients should be appropriately changed. So once you update here the update goes along all the interior cells. Now for all these interior cells, only on the south boundary, you are changing it at 2 times dy. On the north and east, you have Neumann conditions. So whenever you have a Neumann condition, the coefficients will essentially go to 0. So I am keeping them to be 0. And when it comes to the west face is again an inflow condition. When you have an inflow condition, in this particular case, ideally you should have something similar to this on the west face. But then instead of dy, you will be having dx. For this particular case of boundary layer equations, if you recollect the governing equations, you will essentially assume del u del x to be negligible. So your mu x will be 0. So you will be having only dy term. So I am taking dx to be 0. So I have not written anything there. Otherwise, you should be keeping this value as well. Once you update all your coefficients, the next step is to update your mass imbalance term. Mass imbalance is essentially f east minus f west plus f north minus f south.
Sir, in my above JW ny minus ny,
Sorry.
in JW ny plus half or ny
So
minus.
this will be 2 to 2, and this will be from
Start index will be
2 to ny plus 1. Yeah, thank you. But if you won't be needing it since dx is 0. Yeah, your mass imbalance term is again straightforward, east minus west, north and south. So now AP is A east plus A west plus A north plus A south, and then you also have to add these terms. So this should automatically take care of your boundaries as well. Now I have updated the boundaries also. Your AP will be updated with boundaries. And your B is your additional source terms if you have any. Here we have just the pressure term. So the pressure is P current 1 minus the P east, PP minus P east. So this is like when you, I've just passed in a parameter called P star that stores these values. So I'm just writing P star here. And then your du is, this is the coefficients that will go into your pressure correction equation. So that is delta y by AB divided by alpha u or alpha p. So this is your under relaxation. Now it's very similar for the v velocity. The only difference will be here, instead of u, you will be dealing with v. But more or less it will be similar. So boundary conditions, as you have aware, like east is high Peclet number. So you just, it's similar to Neumann condition. West is again 0 component, and then you have north and south will be similar as your u component. This is your mass imbalance, and everything else is similar. Now you have the coefficients for u and v. The next step is you have to solve these equations, and then once you solve the equations, you have to update your pressure correction equations. So now for the pressure correction equations, I need to update my coefficients. So pressure correction equations is straightforward. So you have to just take the values of A east, A west, N north, so A west and all of them. You don't have any B terms. The B term is essentially a mass imbalance. So mass imbalance I am calculating here. Rho times U I minus 1 is your west, U east minus U west. So this is since your mass imbalance in the pressure correction equation has a minus. So if you recollect your pressure correction equation, so you'll have something like AP times P prime equals some sigma NB times P prime NB, and then you have some B term where this B term is essentially minus of mass imbalance, or F east minus F west plus F naught minus F south. So I am just writing that here. So it is rho times U west. So maybe I forgot. Rho times delta y times this, and rho times delta x. Rho times delta x times V star. This is V south minus V north. So that will give you my mass imbalance. And in this particular case, we are essentially keeping the outlet all the boundary conditions we have given are velocity boundary conditions. So you will not be able to solve them directly. So you need to specify some reference pressure somewhere in the domain. So I am specifying my outlet pressure to be 0. So how do I specify that outlet pressure to be 0? I am just essentially keeping all the coefficients to be 0. So when I will actually try to solve the Gauss seidel, it will, all the terms will essentially go to 0 if all the coefficients are 0. So I am keeping all my coefficients to be 0. Sol is where your Gauss seidel is present. So this is very similar to what we have. So you just take summation of A and B times V and B, and then you update this, like as we have discussed previously. Whenever you are using under relaxation, so instead of directly taking the value, you will just multiply it with the corresponding relaxation factor. So depending on this factor, you will only take partially the update from the current one and another portion from the previous value. So phi ij will have partial value of temporary and then also the previous value of phi ij. So where I am limiting my your maximum number of iterations. So when I try to solve this using Gauss seidel, so you will not, I am not actually solving it till the error is within the tolerance. I am actually most of the times it will be limited by this maximum number of iterations that you can do. Now comes the simple. This is where your main part is. So first step is you assume some velocities, but they won't be of any use. With whatever velocities you have assumed, you will solve it. After solving, you get your U star. U star is a solution of it, and I am updating my residual. Once I solve U star, I will solve for the V component also, and I will get V star. After getting U star and V star, I will update the coefficients of pressure correction equation using U star and V star, the latest values I have, and then I will solve my pressure correction equation and get my P prime. Once I get the P prime, I will update my P. P essentially P star plus P prime times some relaxation factor. And similarly, your U correction is again U prime. How do you get U prime? Is du times P prime. So use that equation. So essentially, if you are following the lecture notation, so U prime is essentially dE times PE minus PP, PP minus PE. It's right here. So if you are following the notation followed in the class, so you have UE prime given by dE times P prime P minus P prime E. Okay, this is capital, so something like that. So that is this equation. Similarly, once you update your U, and then okay, I haven't done any correction relaxation here. If you want, you can do the same. So you can multiply this with
U correction, V correction. We didn't apply any relaxation factor.
Yes, if you want, you can apply that as well. You can apply relaxation factor. Usually, you don't have to, because most of the error comes, it taken care here in your P prime itself, and you are carrying it again here. So if you want, you can apply correction here and here, both the places, to be on the safer side. And then the next step is you need to update your boundary conditions. So if you have seen in the previous ones, we are defining a grid in a way that it is storing all the boundary values, and west and south boundaries are fixed boundaries, so you have constant velocities or zero velocity, so I don't have to update them. I have to initialize them at some point. And similarly, north and east are diffusion boundary conditions, like high Pecklinium resistance, where your Neumann condition is there. So the basically this condition is like, if you have nx plus 2 as my boundary cell, u nx plus 2 should be equal to u of nx plus 1. So this way I am ensuring that the Neumann condition is satisfied, so that the gradient is 0 along the x direction. So that is this particular line. And similarly for the v component, I am doing the same. So this I will do both on the top and the right boundaries. That is where my Neumann conditions are present. Once I update the boundary conditions, then I will update the value of previous value to be the current value, u old is u, and all these values. And then you keep on iterating this. So iteration is something I have done in the main loop. So in the main loop, you need to give your boundary conditions. So by declaring the matrices, all the values of velocity are initially 0. Only the inlet velocity should be present, and this should be present only on the west boundary. So this is the west boundary. So maybe I can write 1 to n by plus 2. So on the west boundary, you take your inlet velocity as u, and initially these are some initial guesses you give, but by now I think you are familiar with the technique that simple doesn't actually give you much preference to your initial velocity, because that gets vanished after one iteration. So however good guess you give, that goes off in simple. Okay, there are no, I am not giving any pressure gradient. Basically I am assuming normal boundary flow where your pressure gradient is 0. If you have a pressure gradient, then you need to specify that as well as your initial guess. So this p is essentially all are zeros, so that is the initial guess I am giving, and then you call simple, so that will do all this solving like we have discussed. So first it solve x momentum, y momentum, and then update your pressure correction equation, solve for p prime, u prime, and then p prime. From there you get u prime, v prime, and update your u and v, and then you keep iterating till the error is within the limits that you specify. These are just some helper functions. You solve all of them and then you print all of them. So it takes a little while to run, so I am not running the code. Maybe I can run to show you how it works, or I'll just give you the results directly. Pressure is more or less, so maybe we have to see this. So I've just plotted u versus y. So it's straightforward. For a boundary layer equation, you might have assumed, like you might know already, that after a certain point u reaches a maximum velocity that it has to reach. I've used a hybrid scheme, and the Pecklin number is quite low here, so you might expect some oscillations. I've not tried actually to refine the mesh and see if the oscillations go down, but I'll post the code so you can try all of that and see if it actually converges or not. So is this clear, or are there any questions in this implementation?
Yeah.
Clear. Okay. Now the main drawback with this approach, as you can tell right now, is this is only for structured meshes. So if you have to go to unstructured meshes, this approach will fail. You cannot use this staggered approach. So we have to go to the next approach, call your collocated approach. That is more practical. So just see how you implement in a collocated scheme. So everything will be very similar. The only things that will be different from the previous one and the current one are you won't have to store this along the faces. So horizontal u and v will be stored at the cell centroids. So all of the code remains the same. So these are for my interior cells. So now previously I was storing nx plus 1 to ny plus 2. But now since u is also stored at the cell centers, I am just taking nx plus 2 times ny plus 2, that include both the left, right, top, and all the boundaries also for uv. And these are my phase velocities. So I am storing this because you have to do that momentum interpolation and store these values. And these are the values that you will use in your mass imbalance calculation. So I am storing those in separately. U hat, v hat are your, if you recollect from your class lectures. So basically u hat is sigma a and b times u and b plus b by kp. So this is your u hat. Similarly your v hat. where A and B, U and B are your cell coefficients calculated by discretizing the momentum equation for that particular cell, not the ones that we were doing in the staggered grid. So once you get U star, P star, remaining all the everything else remains the same. The only difference between the previous one and the correct one is how do you actually calculate these convective fluxes. So previously it is straightforward, since your velocities are stored at the phase centers. Now that we have our velocity stored at the cell centers, we need to come up with some interpolation. So how do I do that interpolation? So we'll directly come to simple. So updating the coefficients of u is straightforward. It's very similar to whatever we have done previously. So if you see the u coefficient, so everything else remains the same. So you just use a hybrid scheme, or if you're familiar, if you're convenient using just the upwind scheme, you can just write the first one and then leave the second part. So you can just write maximum of 0 comma minus fe. That will do for the upwind scheme. So everything else remains the same as previous. The only update I am doing here is calculate u hat and store it for that particular coefficients I calculated. So u hat is this sigma a and b u and b by ap. Once I calculate this u hat, I have for all the cells. Now how do I do my interpolation? I solve these equations and I get my u hat v hat. So uf is the phase velocity on the x direction, is essentially up plus u east plus dE by 2 times, this is essentially the d east calculated. I am just since I do not have the value at the phase, I am taking average of I and I plus 1 cells to calculate that. d east you, okay, maybe I will write the equation here so that you can recollect. So u east is interpolated as u hat p plus u hat p by 2, and then you also have some dE times your pp minus p east. And since I do not know the dE directly, I am just taking an approximation here, dE to be half of dp plus p east. Similarly for u and v, once I calculated my phase velocities, then I will update my convective flux. Essentially my f east, f west, f north and f south. After updating them, I will update my pressure correction equation. So here the coefficients are again straightforward. So this is very similar to whatever we have done previously, updating the coefficients. And then once you update the coefficients, you solve for your p prime. Once you get your p prime pressure correction terms, you have to update your phase velocities. After updating the phase velocities, again you update your convective flux, and then this is an optional. If you want, you can do update your cell velocity, or you can just leave it as it is. These are for the boundary conditions. So similarly as previous, the top and the right boundaries are Hyperclear number assumptions, so you have to update them to take care of in the next iterations. So remaining everything is same. So this is clear. It is to a very similar profile. Okay, these graphs are, maybe I should have plotted for the entire domain. Should have reduced this. Maybe this should be clear. It introduces some oscillations, so you can try. Actually, I'll post the code. You can try refining the mesh. So I've just used a very coarse mesh. This takes a little longer to run. I've used very low values of relaxation factors so that it just won't shoot up. So you can try refining the mesh and then see if results will actually converge. Are there any questions in this approach or any doubts? It's straightforward, very similar to whatever we discussed in staggered grid. The only difference is you don't store them on the faces, you store them on the centers, and instead of using direct interpolation of for the phase velocities, you just have to consider these pressure terms as well. That's the only difference. Everything else is same. Simple? Yeah. So the next question is a little different. Or we are just going a little step now. That simpler are already discussed. The next step is you have some of these schemes that we are discussing in the lecture. So you have an up and difference scheme, and then you also have something called quick scheme. So this particular code is a demo of your how to quick and UDS. So maybe we have to describe you what the problem is, and then we'll come back to code. The problem is very simple. You just have a domain something like this. Your governing equation is this, your domain is this, so where you have phi equals 0, phi equals to 1, and these are Peclet number tends to infinite or high diffusion boundary condition, outlet conditions. So we have to solve this equation, and my velocity field is also given to me. The question asks you essentially to calculate the or plot phi as a function of y at x equal to 0.5, or say at some location around the x. This is discussed in the class as well. So ideally you would expect phi to be, so this is my value of 1, this is 0. So at y equal to 0 it is a value of 1. So you would expect it to be 1, and then you would expect it to be 0. This is something that is expected because you don't have the diffusion term here. In this particular case you have gamma equals 0. So when you don't have your diffusion, you do not expect phi to mix here and there. So you would expect some profile like this, which will only along the section you will have more or less a constant phi, and then it should gradually drop to 0. But then when you try to solve these equations with any of the schemes that are discussed in the classes, you will have to see what happens. So the first scheme you can try is a central differential scheme. So okay, do you think the central difference will work before actually trying to solve it?
Sir, can you solve the assignment 11 questions, sir? Assignment 11 1 to 3 questions.
Actually, I am not allowed to solve the questions because the deadline is not yet over. But you have any specific question, then I can help you on that.
No, sir. Week 11 deadline is over, sir. Week 11.
Week 11, not actually.
Okay, week 11.
So what exactly is the question? It's like, can you share your screen?
Yes, sir.
Yeah.
1 minute. sir.
Yeah, I can see your screen.
Yes, sir. This is the. Is my screen visible, sir?
Actually, I can't see the questions if you are sharing something. Okay. Yeah, I can see in my. Okay. Maybe let me share. If you are sharing through phone, maybe I can share. So let me share.
Yes, sir. These are my questions. One, two, three questions only. For the first question, I am not understanding how to do the standardization.
Yeah. Yeah. So this is a question, right?
Yes, sir.
Okay. So you want to solve for a discrete. Okay, maybe let's take this question. So you are facing trouble with respect to momentum equation, right?
Yes, sir. Momentum equation.
Okay, let's start with the momentum equation. So the momentum equation is solved on your phase centroid. So let us say we are writing for the A cell.
Okay.
So I'm writing for this particular cell. So it will be somewhere between this and this. So my equation goes as minus del p del x So the question asks you to consider this as your source term. So if this is my source term, the first step is to, again, you have to linearize it. So how do you linearize your source term? Sp plus phi, but in this particular case, what will be the value of phi? Phi is essentially your u, right?
Yes, sir. Yes.
So how do I calculate Sp?
dou by
So you have to do this at particular u star. So if I were to do the same, so my S is minus half 0 u square. So ds by du at u star 0 u star. So u star is some constant. So my S will be S calculated at u star plus ds du u star times u minus u star. So this is minus half c u star square, and then you have u star times u minus u star. This gives you clear. So your SC is basically 0 u star square, and your SP is minus 0 u star.
Okay.
So from now we will just use the normal one. So I have del p del x plus some c SC plus SP times u equal to 0. So say an SCR from this. So if this is the equation I want to discretize in this particular domain. So this is at x equal to half to x equal to 3 by 2, or what is the delta x? This is 0.1. This is 0.1.
Yeah.
So let's say this is x1 and this is x2. So instead of half, and this will call x1 and x2. So how do you do your discretization? You just integrate from x1 to x2
Okay.
minus del p del x dx plus you have sc plus spu dx x1 to x2. So this first term will be minus of p2 minus p1. Dx will anyway, this essentially will become dp, and this is your first term, and sc times integration dx x1 to x2 is delta x plus how do we write for the second term?
UA delta x.
So your midpoint is a, so you just write ua times delta x. So now you have to solve this equation. So do I know p1 p2? I think there would be an initial guess given to you. P1 p2 are zeros and ua etc are also given. So if you solve this equation, you already know sc and sp from these equations. So your previous value of u, you will use that to calculate u and ub, like that is your initial guess of u and ub, 0.5. So you will keep 0.5 and then calculate sc and sp. So your u star is essentially 0.5. From there you calculate sc sp, you substitute here, then you will get a new value of ua. But ideally you wouldn't be solving this equation directly. This is your equation, first equation, like for your x momentum. So now what does the question asks you? You have to apply this. Okay, what is your next step? Is to get your pressure correction equation. So how do I get my pressure correction equation? From this. So how do I write ua prime is some d times
P2 minus P1.
P2 prime minus P1 prime. So what is the value of this d? So I'll just write dA. So what is the value of dA? You can get from this equation, right? From this equation.
Delta x by
delta x by or 1 by sp times delta x, right?
Yes sir, yes sir.
So this will be your dA. So this is your pressure correction equation. But you need to get other equations also. So you have another equation also, right? If you discretize for this cell, you will get one more equation.
Yes sir.
So similarly, you will get one more equation for p3 prime and p2 prime. So now we have two equations and three unknowns. So you need to specify one of these. So which one do you specify? Like since only velocities are given, you can either assume p3 prime to be 0 or p1 prime to be 0. You can assume one of them to be 0. Then you will have two equations, two unknowns.
We have given continuity equation, sir, by using continuity equation.
Yeah, your continuity equation will just give you ua prime equals to ub prime, right? Or does it give you anything else? So your continuity equation will give you, sorry, not ua prime.
So
this is what your continuity equation will give you, right?
yes sir.
So basically two equations you will be having. So you will only have two equations, but then you have three unknowns.
Okay. That means UA can be up to UA and UB can be up to as UA star, UB, UA prime.
Yeah, that is what you will get. So when you substitute UA and UB like this, and then you apply your continuity equation. So these are your continuity equations. So from this, what is the expression you will get? UA star plus UA prime is essentially 1. So that gives you dA times P2 prime minus P1 prime plus UA star equals 1. So this is one equation. Similarly, you will have dB times P3 prime minus P2 prime plus UB star equals to 1. These are two equations.
Okay.
But what are the unknowns? P1 prime, P2 prime and P3 prime.
Yes.
So you have three unknowns and two equations.
Okay. We need to solve another domain G for another cell.
So no, your momentum equation you can apply only for two cells, right? You have only two cells to apply for.
Yes, sir.
So what do you do then?
Oh, that,
Basically you have to assume one of these corrections to be 0.
okay, sir.
So your third equation will be either p3 prime equal to 0 or one of these, any one of these to be 0.
Okay.
You assume one of these to be 0, then you will have two equations and two unknowns.
Okay.
Then you can get your p prime. Once you get p prime, from there you can calculate your u prime. From there you can update your velocities, and then you can do your simple iteration. Like it asks you to only one iteration, right? Or two iterations. To perform iterations using okay, it asks you to perform some iterations. So from there you can take it on. The problem is like this. So when you have your domain and only your velocity initial conditions are given, like all the boundary conditions are given in terms of velocity, then your pressure is arbitrary. Like your equation is only dependent on pressure gradient and not the actual value of pressure. So you will get some indeterminate equations. You have to assume some pressure to be 0, that is your reference pressure, and only then you will be able to solve these equations. So this is the only question you are have doubt with, right? Or there are any other parts of it?
No, sir, that is the only question.
Okay. As far as the code is concerned, I think it is uploaded in the lecture notes. You can go through the code as well, but it is in Fortran. So the course instructor has uploaded a code as well, so you can check that to see if the value you get is matching with this or not. So this is clear, right? Are there any questions in this?
Yes, sir.
Clear? Okay.
Yes.
So coming back to the problem we were discussing. Yeah, so if this is the domain and this is the governing equation, can you solve it using CDS? Or if I write the coefficients, you have something like this. Say it is a 2D domain, but you will have A naught and A south also. The question is you want the coefficients to be positive, so you essentially require dE minus Fe by 2 to be positive, which will happen only if so this is your reason you have to use affine scheme. Sorry, that is your F is less than 2 times dE, so your Peclet number is less than 2. Only when your Peclet number is less than 2, this particular A East coefficient will be positive. So in the current problem, your gamma is 0, which means your D East will be 0. So your cell Peclet number will be infinite. So if you try to use your central differential scheme for this problem, it will just fail because your Peclet number is actually greater than 2. So we have to use some of the other schemes. Either you can use affine scheme or quick scheme. So I think quick is already discussed in the class, right?
Yes, sir.
Yeah. So how do I use the quick scheme? So if you have phi east, if you have F east to be positive, in an affine scheme we just consider phi little e to be P capital P. This is in affine. But in quick we will use a higher order approximation. So it goes something like this is and then you also remove the quadratic term. So This is for if F is positive. So this is something you use in a quick scheme. The problem here is also very similar. Now you can see the coefficient of the coefficients can go negative, right? You have a minus 1 by 8 term coming for phi west. So here again you might have coefficients to be negative. What is the problem with the negative coefficients? So why do I not, like, why am I worried about negative coefficients? It's because your Scarborough will not be satisfied. So you have sigma A and B by AP should be less than or equal to 1. If you have negative coefficients, then sigma A and AP will be essentially sigma A and B. Usually we write it in this way. Minus if you have source terms, you have additional terms. Say we do not have any source terms. In that particular case, if you have negative terms, and when you consider the mod summation of all the mod values versus the actual summation of them, the negative values will try to decrease the value of AP, and then this particular term will be positive, will be greater than 1, and then your Scarborough will not be satisfied, so that your Gauss-Seidel will not work properly. That is one problem with this. So we tend to avoid this negative and negative coefficient. So the approach we use is deferred correction. I think this is also discussed in the class. So deferred correction approach is discussed, right?
Yes, sir.
Yeah. So the idea is straightforward. So what you do is, if you want to update something, you consider the, it's simple, you consider an upward one and then you delete it, plus your quick scheme. This is something that you do at the current value, and these are your star values or the previous iteration values. This way you will solve it. So I just want to show with this, maybe we can conclude. So how do you implement it? So these are just some helper functions. The only thing that we need to consider now is how do you update this. So F east, F west, F north, F south are where you have to update them appropriately. So this is a CDS. Since we know that for this particular problem CDS won't work, I am not showing, but the code is straightforward. So okay, we will start with UDS first and then we will go to quick. So how do you do it in a UDS? Your A east is maximum of 0 comma minus F east, A west is max of 0 comma F west. So these are straightforward, and then depending on your boundary conditions you update your A east and west. Like I have used high Peclet number on the north and the east boundaries, so I am making the coefficients to be 0. So the next, in this particular case we do not have any diffusion term, so I am not adding A west and A south. Otherwise you have to consider A west and A south, and then like we have discussed previously, you need to multiply like change the coefficient to be 2 times dx or 2 times dy. Here since diffusion is 0, I am not doing that. Then AP sigma A and B plus your mass balance term, and then you just solve it. Solve is very same as what we have discussed previously. So this is the same code that I have used for the Gauss-Seidel. UDS is straightforward. In the quick scheme, what you do, you update your coefficients same like before. It's like basically in deferred correction we use an upwind scheme, and then you remove the upwind and then add a quick scheme. So these coefficients are initially updated same as your upwind scheme, but then inside that, when you try to solve the equation, you have to add and remove the upwind and higher order scheme. The higher order is essentially your quick. So what do I do here? You are having a half of phi east plus phi p plus phi east minus 1/8 of east plus west minus 2 times phi p. So this is a contribution only from the east cells. Similarly, you need to add contributions from the west, north and south cells appropriately in the correct direction. So in the F west you will have an area term that will go into minus, so I am just writing minus FW, and similarly for the F north it will be positive and F south it will be negative. Now these are all done only for the structured meshes. So when you have an unstructured mesh, is something that I have not discussed the code here, but we discussed in some of the previous ones. When you have unstructured mesh, you do not know you do not have this east west north south relations. in those particular cases, while storing the fluxes, you will have to consider the area vector and then store the value appropriately. So then all of them will be plus. Now that we have fixed what is f east and f west, I have to take care of these plus and minus signs in the code. Otherwise, usually it should be taken care by the area vector. So you have to store the area vector for each of the cells and then appropriately multiply it with the central vector and then get the sign of that and use that here. So this is for a higher order term. So this is a quick term, and then upper term is straightforward: east minus west plus north minus south times p. And this particular deferred correction approach, everything is assumed to be in the star values or the previous iteration value. So this will go into my b term instead of my AP or A east, A west, A north. So I am adding them to the b term, and then I will solve the equations using Gauss setting. Simple and straightforward, right? So are there any questions in this, or is it clear? Okay, I can show you the result I got. So both quick and UDS are kind of like, we have seen it should ideally be a straight line, something like this, but then the methods introduce some false diffusion. So even when D is 0, they tend to show you this diffusion behavior. So this particular problem cannot actually be solved using CTS, but if you have a variable velocity field so that your AP is essentially not 0, then you can try solving it using a central difference thinking, and you can see some oscillations here and here. It will actually oscillate instead of giving you the straight value if you are using central difference. But this cannot be solved using central difference, so I am not able to show that. You can change the problem a little and then see if it actually gives you the fluctuations and how to dampen that fluctuation. Then you can see quick will not give you any of these fluctuations. Quick and UDS will not give you fluctuations like the central difference does. So yeah, this is pretty much clear. Like, are there any questions in this? So deferred, no, right? Yeah.
Yes. Yes.
Yeah, that's all I have for this week. So if you have any questions, we can discuss them. Any specific questions regarding the course or any programming that you want to discuss? So basically, I asked for an extra session in the next week as well. So if you want me to discuss any specific programming problems or any practical, of course there was one question previously to discuss one paper and then see how FEM is actually implemented nowadays. We can have that discussion, or if you have any other questions, we can discuss them as well. You can let me know now, I can come prepared for those.
Okay.
Nothing?
No, sir. But that means for a medical applications like blood flow or bifurcation, like examples like bifurcation, that means for applying the CFD, is there any books for reference, sir?
I am actually not, okay, I am not actually an expert, or like I cannot comment on that. I am not aware of that field.
Okay, what are the best books for FPM, sir, for finite volume method?
So the references are already provided in the lecture. So basically Patankar is the one who founded this technique. So he has a book on that. So you can go through that book, Computational Fluid Dynamics by Patankar.
Okay.
The entire book name is already present in your course main website itself. So you can see you can get that book online. Also, it is available online. It discusses some other problems also. So the ones that we haven't discussed in the class. So you have some curvilinear meshes, for example,
Sure.
something like that, and then you have some multi-grid approach, that is also something that will be discussed. You can go through the book. Unstructured meshes is something that we haven't given that much attention to, but then I think I have solved 2 or 3 problems, but not more than that. Book gives you examples
Sir,
of
can
them.
you give example for multi-grid mesh? How to solve a multi-grid mesh?
Multi-grid, okay, then maybe we can take multi-grid as an example in the next week.
Okay.
But then, okay, I can just give you maybe for a 2D one, but for a 3D problem will be a little difficult to solve in the class. So like with the hand calculation, so that the idea is to get you exposed to the method, right? Maybe we'll take a 2D problem and then we'll see how to apply it. So unstructured is clear. So okay, then we'll take up multigrid in the next week. And then what else do we have? Any other?
No, sir. Clear. Up to now, it's clear.
It's clear. Okay. If you don't have questions, then maybe we can conclude the session for today. Whereas there is no one else to ask questions. Okay then. We'll conclude since there is no one to ask questions. Yeah, thanks for joining. We'll discuss
Thank you, sir.
multigrid in the next week, same time.
Okay, sir. Thank you, sir.
Thank you.
Sir,
You were asking something?